Good morning. Uh, Welcome for today's session on fundamentals of heat transfer. And here today we will try to cover um, Module 1. And in Module 1, we will try to go through some of the basics of fundamentals of heat transfer. And in this case, like before we start with the particular subject, we need to understand why exactly we need to study heat transfer. Now, before your sixth semester, you have probably studied basic thermodynamics and applied thermodynamics. And in both those subjects, you have come across problems where you are trying to find out some kind of an energy analysis of a thermodynamic system. So maybe initially you have done it for like a simple system like a piston cylinder arrangement and all. And later on in applied thermodynamics, you have done so for more practical type of thermodynamic system like a turbine or a boiler or maybe a condenser or other heat exchangers. Now in all those scenarios, you have probably studied only how to do the energy analysis. That means what part of the energy has been converted into useful work, and if so, how much energy has been rejected into the environment as a waste heat. But what insight does heat transfer gives us is that the rate at which those particular energy transfer takes place. Now, why this particular information is important for us, like at how fast or how slow the heat transfer is taking place, or the heat is moving in or out of a system. We need to understand that because when it comes to heat transfer, it's all about designing a particular thermodynamic equipment. Now, before this, in your basic thermodynamics and applied thermodynamics, you have not at all come across a situation where you need to give design specification with respect to whether a turbine or a heat exchanger or anything of that regard. But in this particular case, with that information, like how fast or how slow the heat transfer is taking place, we can come up with certain design specification for our system under consideration. Now you have to understand is that uh, the problems can be of many different type. We just need to understand how the questions will be presented to us. So I will just take an example to illustrate my point. Let's say we have a furnace, and let's say we draw the furnace. And let's say we have a roller at the two ends of the furnace, and let's say we are rolling a certain sheet metal over the roller. So these are the rollers, and this is the furnace. Now in this case, you see the question can be presented in two ways. Let's say the sheet metal is going inside at a temperature of 30 degrees Celsius, and the job of the furnace is to heat the sheet metal to a temperature, let's say 750 degrees Celsius. Okay, now this is the condition that has been presented to you. Um, and you have to come up with certain design specification of the furnace. So that means how long, let's say the first type of question that can arise is that the rollers will rotate at a fixed speed. Okay, the rollers will rotate at a fixed speed In that case, you need to know how long should be the furnace. Okay, so this is sorry. Um, so you need to know how long will the furnace be. And the second type of question is that suppose you have a fixed length of furnace. Fixed length of furnace. In that case, you need to know how fast the roller will rotate. Okay, so this is just one scenario where we can use the concept of heat transfer uh, to really understand what goes uh, in designing a particular thermodynamic system. Same thing we can also put like let's say we have pipe, and in this pipe let's say fluid is entering and fluid is exiting on the two ends, and let's say some steam is condensing. Okay, let's say some steam is condensing in this particular pipe, and because of the condensing of the steam, the latent heat will be given to this particular fluid, whichever is flowing. Maybe it's a water or maybe it's some other kind of fluid. We're not bothered with that. In this case, let's say the steam is entering at 30 degrees Celsius, and it has to go out at 60 degrees Celsius. Then you need to know again the question can be presented, how long should be the length of the pipe. Okay, also in another scenario is that if length of the pipe is fixed, if length is fixed, if length is fixed, then in that case what should be the mass flow rate. So please forgive my handwriting a little bit because I'm writing on a pen tablet, and this is my first time of using a pen tablet, so it is really uh, a little bit difficult for me to adjust to the situation. So this is what it is like to study heat transfer, and this is the reason why we need to study heat transfer, because we get an idea about how to come up with the design specification of any thermodynamic system, which we have not done so far in our basic thermodynamics and applied thermodynamics. Now let's say we would like to uh, I could use a bigger yeah. So in this case now let us start talking about what are the laws that incorporates heat transfer. Okay, Now, when it comes to laws, work transfer, I mean, in your basic thermodynamics, you must have studied heat transfer, and I mean, like heat and work, like little bit of concepts about heat and work, and you have probably come across the modes of work transfer, so through electricity, and there are definitely other mechanical ways also through which we can transfer work from system to surrounding or from surrounding to system. A piston cylinder arrangement is a very good example for work transfer. So there are many modes of work transfer, but when it comes to heat transfer, we have only three modes. The first modes is your sorry. So first modes of heat transfer. So in this first mode is your conduction. We will have a detailed discussion about that a little later on. Conduction, and then you have convection, and the third one is your radiation. Okay. Now each one of this mode of heat transfer is governed by a subsidiary law. All right. Now what exactly are subsidiary laws and what are exactly fundamental laws? Now fundamental laws are the laws which goes into any kind of application or any kind of thermodynamic analysis. These will be common uh, depending upon like no matter which particular scenario you are taking, whether you are taking conduction, convection, or radiation, fundamental laws has to be satisfied. You cannot say that my situation satisfies only subsidiary law and it does not satisfy fundamental law. Okay. So like if you take a scenario where conduction is dominant, so definitely laws, subsidiary laws related to convection and radiation will be ignored in that. But fundamental laws in that case has to be satisfied. You cannot say that the fundamental laws are ignored. All right. So fundamental laws are those laws which has never been disapproved either through experimentation or through analytical calculation. The three fundamental laws that we have that we need to deal here is first one is your continuity. So this is a continuity law or law of conservation of mass, and you have already studied that in your fluid mechanics. So any steady flow devices, mass in is equals to mass out, and if it is not a steady flow device, then the change in concentration of the or the amount of mass stored in the system will be nothing but the difference between the mass out and mass in. All right. So there may be either a decrease. If it is not a steady flow, then there may be either a decrease or increase in the mass of the system, uh, depending upon how the flow is happening. All right. So imagine like a tank is there, and if uh, 2 kg per second water is entering into the tank and 2 kg per second water is leaving the tank through another pipe, then in that case, the amount of water stored in the tank will be zero. Whereas if you have a scenario where the inflow is 5 kg per second and the outflow is 3 kg per second, then in that case, the water stored in the tank will be 2 kg per second, just the difference of this. All right. The second one is whenever whichever system we are discussing has some kind of an unbalanced force involved in it, maybe pressure, maybe some other dynamic forces involved in it. In that cases, we have to satisfy Newton's law, second law of Newton. All right, the momentum equation that usually comes into uh, scenario. So we have to satisfy that. Um, right off the bat, I can say that that in our study for heat transfer, we will hardly come across any scenario where we have to deal with Newton's law. But yes, definitely continuity law, and the third one, which is the most important one as far as heat transfer is considered, is your law of conservation of energy, or first law of thermodynamics. All right. So you already know the energy can neither be convert this one. Sorry, energy can neither be created or destroyed. It can be converted from one form to another. And law of conservation of energy exactly says that. So these are the fundamental laws which has to be satisfied no matter whether you are dealing with a conduction, convection, or radiation scenario. Now, since fundamental laws are out of our discussion as of now, so we can focus more on the subsidiary laws. The first subsidiary law. So I will just erase this. That there is a problem with the software, I guess. It's not erasing properly. Rather than erasing, I think we can just move on to the next page. And I'm using it for the first time, so guys, please. All right. So let us go into our discussion for modes of heat transfer. So let us start with conduction. And in conduction, the subsidiary law that comes into play is your Fourier. All right. And before we discuss Fourier's law, we would try to have an idea of exactly what is conduction and how exactly it takes place. So conduction mostly happens in case of solids. It does not mean that it does not happen in case of fluids. We will discuss that a little later on, but mostly in solids. So in solids, the atoms will be arranged properly in an array, let's say. And let's say this is just a description of a metallic bar, okay, which is heated with a burner on one end. Now, let's say what will happen. See, all these atoms are vibrating in their own place. This happens. Vibrational energy. This vibration will cease to exist only if the temperature of the body reaches absolute zero. Now, according to third law of thermodynamics, we know that it is not possible in a real case. So definitely all the atoms, it doesn't matter whether it's a part of any non-living thing or living thing, all the atoms will technically keep on vibrating depending upon their temperature, and the vibration or the intensity of vibration will be increase or decrease depending upon the absolute temperature of the body. That's classical physics. So in this case, this vibration will continue, and since you were heating the metallic part, so definitely the vibration will tend to increase on this side. All right. Now when the vibrations are increasing, there is a chance that there will be collision between the atoms, and as a result the vibration will be passed on to the next atom, and so on and so forth. It will keep on traveling. The vibration there, while vibrating, it will collide, and the vibration will travel from one end to another end. And this is how the heat will move from one end to another end in the metallic bar. But you have to understand that when it comes to solid, we have two very distinct classification. One is your metals, and another is your non-metals. We are not going to talk about semiconductors here. We were just keeping a broader classification, metals and non-metals. So in case of metals, you will see that heat will transfer very fast. If you take an example like an aluminium or even iron, are very good conductor of, or copper are very good conductor of heat. Whereas if you see glass, uh, ceramic, so these are very bad conductor of heat. All right. So what exactly changes between these two? So why one is good and one is bad? Because both are solid, correct? And vibration is taking place in both of them. So this is where we have to really look into how the heat transfer or what percentage of heat transfer is taking place with respect to vibration. So if we go for a definition of conduction, it happens because of exchange of energy between molecules, all right, due to lattice vibration. All right, so this is called as your lattice vibration. Now lattice vibration constitutes 25% of the energy transfer. Remaining 75% depends on something called as a free electron. Now we very well know that free electrons are only present in case of metals, and that is why metals are a good conductor heat or other forms of energy. So remember the definition for conduction would be, this is the mode of heat transfer where the energy is transferred due to lattice vibration and also due to presence of free electron, depending upon whether the heat transfer is taking place in case of metal or non-metal. See, I don't really bother about what exactly the definition is written in a book, as long as you understand it, the physics behind it. If you completely understand it, and if you write it in your own words, and if you write the correct thing, uh, I will give the same marks. All right, so no need to memorize, just try to understand what goes inside a particular physical phenomena. All right, so this is about conduction. Why it's not selecting? So let us talk about convection a little bit. And before I start the next session, I will just get a little bit more familiar with the software so that I can easily concentrate on the teaching, because here I'm spending more time concentrating on the pen tapping. All right, fine. So let us go into the second mode of heat transfer, which is convection. Now in convection, it usually happens in case of fluids, and by fluids I mean it can be liquid or it can be gas. Now in case of fluid, we know that the molecules are free to move. All right, and this is why convection heat transfer happens, because of bulk motion of molecules. Now you see, uh, let's say we have a cup of coffee. All right, we have a cup of coffee, and let's say the coffee temperature is around 80 degrees Celsius. We kept it in a room which is at 30 degrees Celsius. So you see, this coffee cup is surrounded by air molecules, correct? Now these air molecules, what will happen is that they will come in contact with the coffee cup, and those molecules which are in direct contact with the coffee cup will get heated up. Now we know that whenever a fluid gets heated up, when fluid heated, density decreases. All right. So whenever density decreases, these molecules, what will happen? They will tend to move up. All right. And as a result, it will create a partial vacuum here. Now this vacuum has to be filled up by these additional molecules, which will tend to move and occupy this space, and will eventually again get heated up and keep on moving upward. As a result, what is happening? These molecules, they are taking heat from this coffee cup, and it will continue till the temperature of the coffee comes to 30 degrees Celsius. So when it becomes equal to room temperature, this motion of molecules will stop. And this particular thing, this motion of molecules, as you can see, they are coming in contact, they're taking away the heat, is called as your convection current. Right? Yeah. Now this is called as your natural convection. Now the same scenario, if I put a fan here over here and drive the wind onto the coffee cup, this will become your forced convection. All right. So this is the scenario with respect to convection. You have to understand that convection is the mode of heat transfer which happens due to the bulk motion of molecules. So even heating a vessel of water or over an open gas is essentially convection. So what happens is that the water in the vessel, so whichever water is water molecules which are in direct contact with the vessel will get heated up first. All right, and as they heated up, they will tend to rise up, and other molecules will occupy its space, and this process will keep on continue until the temperature of the entire water comes to 100 degrees Celsius, and then obviously boiling starts if it's an open vessel. So this is all about your convection. Let us go into the third mode of heat transfer. So first we will discuss the modes of heat transfer, and then we will discuss the subsidiary law that are associated with them. All right. So let us go with the mode of heat transfer. Next mode, so it's radiation. Now, in case of radiation, if you see both conduction and convection, they all needed some kind of a material media. In the first case, conduction needed your lattice vibration, and in the second case, the convection also needed your molecular motion to happen, fluid molecular motion to happen in order to carry away the heat. But when it comes to radiation, you see, we have sun, all right, and we have earth, and there is nothing but a vacuum in between them. But every day, a large amount of heat reaches from sun to earth. And since it has no material media, definitely it can neither be conduction nor be convection. It has to be some other mode of heat transfer that is taking place. So in case of radiation, what we are going to look at is that radiation is already answered with respect to classical physics. All right, it's not like that we are going to I mean, like we have found out about radiation while studying heat transfer. I mean, like as an engineering subject. So, for the classical definition, as I already said, is that every essential molecule tend to vibrate in its place, and these vibration are always there until and unless the temperature is uh, reached to absolute zero. Now, if the temperature of the substance increases, the vibration also tends to increases. And when the vibration increases, they send electromagnetic waves. All right. Now, electromagnetic waves does not require any kind of material medium to be present in order to travel from one location to another location, and that is how the radiation exactly takes place. Now, imagine a surface. We have a surface, and let's say we have two identical surfaces. All right. One it is at temperature T1 and another is at a temperature T2. And let's say, just for the sake of argument, T1 is greater than T2. In that case, the amount of radiation, both are above absolute zero. And let's say about T1 and T2 are greater than 0 Kelvin. Right? So in that case, what will happen is that both will be emitting radiation. But in this case, in the surface 1, let's call this a surface 1, and then this is a surface 2. In case of surface 1, the amount of radiation that is going out will be more. Radiation that will be going out will be more. Why? Because radiation directly depends upon the absolute temperature. And since in this case, sorry, in this case, the absolute temperature is more in case of a surface 1, so definitely it will emit more amount of radiation. Also, as the temperature increases, the radiation of a particular wavelength will be coming out as more. So we will see all those things when we discuss radiation in detail in your fourth module. So radiation is the mode of heat transfer which happens because of the presence of, with the help of electromagnetic waves, and they does not require any material medium to be present. Also, radiation uh, is the only mode of heat transfer where it depends upon the absolute temperature of the body. Now, if you see conduction and convection, when we will go into the subsidiary law, we will see that it more depends on the temperature difference between the system and surrounding. But in case of radiation, it solely depends upon how much radiation is coming out of a body, solely depends upon the absolute temperature of the body. It does not matter what is the surrounding temperature. Just like the sun's temperature is constant, irrespective of whether the atmosphere in the earth changes or not. All right. So sun will send the same amount of heat every day. So that's all about modes of heat transfer. So we will just stop here and we will um, start a new session again in a few minutes where we will discuss the subsidiary laws.